so glad you joined me this evening. We're going to be looking into moving from Lewis dot structures, which are really a two-dimensional representation of the structure, to showing how the Lewis dot structure leads us to the three-dimensional shape. And if we can get to three-dimensional shape, if we can get to the structure, we can start understanding the function. So let's dive in. Hopefully you have already seen a video, hopefully my video, on Lewis dot structures. So I'm going to do these quickly. Beryllium is one that takes less than an octet. And so this would be its Lewis dot structure. Now, let's look at the number of atoms bonded on the center. There are 2 chlorines. There are no non-bonded pairs. So we have a total of, this electron pair geometry counts both the bonded and non-bonded in the description. Whereas when we talk about our Vsepr shape, it counts only the bonded atoms. So this would be linear. Now, why is it linear? Vsepr says that we have valence electrons that repel one another around the central atom. And so these pairs of electrons repel those pairs of electrons, and they want to get as far away as possible. And 180 degrees will do it. So I would call this an AB2 structure. It's linear, and its bond angle is going to be 180 degrees. Let's look at BF3. Again, I'm going to do the Lewis dot very quickly. 3 plus 3 times 7. I'm going to distribute those around the boron, keeping in mind that boron is an exception to the rule of 8, that octet rule. Okay, so I've got 3 bonded atoms and no non-bonded pairs. Vsepr says the valence shell electrons repel one another. So these electrons are repelling one another to get as far apart as possible. And to do that, this is an AB3 structure. They stay in a plane because there's nothing to push them out of the plane. And they form a triangle. The more you can visualize, the less you have to memorize. So take a look at some of the many sites online that show these molecules rotating in space. This would be called trigonal planar. The angles are 120 degrees. And its electron pair geometry is also trigonal planar. That's not always true. So far we've seen that the electron pair geometry and the Vsepr shape are the same, but we're going to see a few examples soon where that's not the case. Okay, so that gets us a start. Let's try some other ones that get a little bit more challenging. Lewis dot structure, this is silane. Man, this stuff, you let this loose in air and you're ready for a fireball. Okay, silane has this structure. Okay, and it's got 4 bonded atoms, 0 non-bonded pairs. Vsepr says these pairs, these bonded pairs, are going to get as far away as possible. And some of you might envision that as a square and think it's 90 degrees. But remember, we have to get into 3 dimensions. And to do that, we form a tetrahedral structure. It's a 4-sided structure. Hopefully in your class, you will get to build these because it's much easier to visualize the shape if you can build models. So this is tetrahedral, and its Vsepr or molecular shape is tetrahedral. I'm not sure if you've noticed a pattern, but so far we haven't had any non-bonded pair of electrons, and my electron pair geometry is the same as my Vsepr shape. This is an AB4 structure with typically 109.5 degrees. Okay, angles can vary a bit depending on the size of the peripheral atom. So you're just going to learn some typical bond angles. Let's take a look at pH3. So phosphorus has 5 valence electrons. Each hydrogen brings 1 for a total of 8. Now we're going to see a little nuanced difference. I now have a non-bonded pair on this central atom. So I have 3 bonded atoms on the central atom, 1 non-bonded pair. This is 4. 4 plus 0 is 4. 3 plus 1 is 4. It's in the tetrahedral family. So the electron pair geometry, remember, is the sum of B plus E, the bonded pairs and the non-bonded pairs. But Vsepr shape wants to envision in 3 dimensions. Sometimes we try to draw that. Let me redraw this and show you how we try to image that. So we'd have phosphorus with 1 hydrogen coming out of the plane, another hydrogen in the plane, and another hydrogen going back behind the piece of paper. And then this non-bonded pair at the top. Okay, this would be an AB3E structure. This is where this shorthand really helps. You're hopefully going to memorize that an AB3E structure is trigonal planar. You'll memorize that if you can figure out the Lewis dot structure and get to that generalized structure, you'll memorize the Vsepr shape. And if your professor or teacher requires, also the electron pair geometry. Now, here's where there's a nuance in our Vsepr. Remember, Vsepr said these bonded pairs of electrons repel one another. Well, non-bonded pair need more room, so they repel more. I'm trying to show that with kind of the double arrow there. Non-bonded pairs repel more than bonded pairs. What that does is it squishes this angle down a little bit. So instead of 109.5, it's on the order of 107 degrees. For every non-bonded pair of electrons, you can take away 2.5 degrees. So if I took away 2.5 degrees, you're going to get, not exactly, but pretty much in the ballpark of the angle that you need. Okay, let's try another one. This one, the ubiquitous water. So I have sorry about that. I have HOH. Now, I'm going to bend this a little bit. You would not normally do that if you did your Lewis dot, but I want to make a point with this. So I've got a non-bonded pair up here and a non-bonded pair up here. So I have 2 bonded atoms, 2 non-bonded pairs. 2 plus 2 is 4. I'm still in the tetrahedral family. And I have an AB2E2. Anything with AB2E2, we're going to call bent. Okay. Now, do you remember that I said that bonded pairs repel less? So this has certain repulsion. These non-bonded to non-bonded are the most repulsion of all. Okay, so those bend the angles even more, push the atoms closer together, and we get an angle on the order of 104.5. Take away another 2.5 degrees from 107, you get your 104.5. Okay, now I have arsenic, and I've got 5 bromines around it. Okay. And all of those have a complete octet. I'm not going to spend the time drawing that. But you see we have 5 bonded, 0 non-bonded. This is called trigonal bipyramidal. And it's an AB5 structure. This is also trigonal bipyramidal. And it has angles of 90 degrees. If I could maybe draw this slightly different now that you can envision it, I wouldn't have expected that out of a Lewis dot structure, but you have an arsenic and you have three bromines, and those first three bromines are making a triangle in a plane. So those bromines are making a triangle. Sorry about my art there, but I'm going to try to envision it. A triangle in the plane. And then you have a bromine going up and a bromine going down. So the bromines in the plane are 120 degrees, and then the they're called the axial, I believe, bromines, those are 90 degrees. Okay. Now, there's all sorts of other nuances. There's one that is a 4-1 structure and a 3-2 structure, and a 2-3 structure. If you're in advanced, they're going to have you memorize those and check those out. I'm going to keep my videos straightforward. I'm going to leave those for an activity or a reference in your class. Selenium hexafluoride has 6 fluorines around it. Each fluorine can have one bond that gives selenium an expanded octet. All the fluorines have their completed octet around them. I'll leave you to draw those. I have 6 and 0. This is octahedral. Again, I implore you to look online and you'll see that there are 4 faces above a plane and 4 faces below the plane for a total of 8. And this is an AB6 octahedral. And they're all 90-degree bond angles. From a fluorine to a selenium to a fluorine is all 90 degrees. Okay. Now, again, we can have 5 1s and 4 2s, and I will leave that up to your class for you to do, or just look up a chart online. And for the sake of brevity on the video, I'm hoping you got the basic concept of Vsepr shapes. So glad you could join me. Take care.